All right, ladies and gentlemen, you are about to watch Chapter 7, Lecture number 4 on periodic trends for Ralston Valley High School AP Chemistry. Much of this lecture will be a review from your atomic theory unit from last year, but there are some new concepts that are tested in the AP exam that are not part of last year's conversations, so we'll make sure to pay extra attention to those as we go. So without any further ado, let's go ahead and get started. All right, we will begin this lecture with a brief review of some nomenclature off of your periodic table, since we want to make sure you can navigate the table quickly and efficiently when you need to on the AP test. Things we're going to go ahead and have a look at on our table here is, to start with, the names of the different families or groups on the periodic table. As you recall, we number those groups starting off from number 1 on the left-hand side through number 18 on the right-hand side of your periodic table. And several of those groups have traditional names associated with them besides their numeric names. The first one that we're going to talk about here is Group 1A, which is otherwise known as the alkali metals. Those alkali metals include things like lithium, sodium, and potassium. Note that the element at the top of that family, again, is hydrogen, which is not traditionally associated with the traditional alkali metals, though, even though it is a group 1 element. It is not exhibiting metallic characteristics unless it's under extreme conditions. Moving along, group 2A, next to the alkali metals, we have the alkaline earth metals. And we're going to go ahead and skip over these elements in the center here until we move over to group 3A, which is otherwise known as the boron group, followed by some other easy ones here. We've got next the carbon group, the nitrogen group, the oxygen group, and then 2 at the end to remember, we have the group with fluorine at the top, which is otherwise known as the halogens. And then finally, group 8A or group 18, either nomenclature is fine. We refer to those as the noble gases or the inert gases. And then looking at those columns towards the center there that we skipped over, you recall from last year, we refer to these as the transition metals. And then the group down at the very bottom right there, we refer to as the inner transition metals. Those, again, are the names of the groups or the columns on the periodic table. The periods on the periodic table are even easier to name. Starting off with the first row on the table, we refer to that as period 1, followed by, not surprisingly, periods 2, 3, 4, 5, 6, and 7. And then again, recall from last year, the 2 periods at the bottom of the periodic table actually aren't their own unique independent periods. Those are referred to as the lanthanides for the elements on the top and the actinides for the elements on the bottom. The lanthanides follow, not surprisingly, element number 57, lanthanum, on the periodic table. And as they're really part of that period, that means the lanthanides are really part of period 6, and the actinides are part of period 7. So we've got the columns, which are the groups, and the rows, which are the periods. Next, we're going to take a quick look at a stair-step line, which separates 2 distinct classes of elements on the periodic table. To the left of this stair-step line I'm drawing, we see elements that are familiar, like, say, copper, nickel, zinc, silver, gold. All of those collectively share a lot of characteristics in common. That is, they're malleable, ductile, fantastic conductors of heat and electricity. These are all properties we associate with the metals. So to the left of that line of division, we have the metals. And to the right of the line of that division, we have elements like oxygen, carbon, sulfur, neon. These elements are elements which are not conductors of electrical current, and they essentially have opposite properties of those metals we mentioned earlier, so we refer to those as the non-metals. And along that line of division, we've got elements that kind of straddle the line between those 2 different general characteristics of elements. And this includes the elements of boron, silicon, germanium, arsenic, antimony, tellurium, and depending upon which book you're looking at, the 2 elements down below there as well, polonium and astatine. One note there real quick, one element that's touching that line, the stair-step line that is not included within this group is element number 13, an element which we consider definitely to be a metal given its shiny, malleable, ductile, conductor of heat electricity, all the things we expect a metal to be. We see elements which are in some cases share some of the properties of metals and some of the properties of non-metals. Elements like silicon being a prime example there, which is itself kind of bluish gray in color, which is kind of a metallic sort of color. It's also kind of lustrous. But on the other hand, it's very, very brittle, which means that it's not malleable like a metal would be. That's more of a characteristic of a non-metal. And also it's a conductor of electrical current, but only under certain conditions. So it's what we call a semiconductor. So those elements that, again, share some properties of the metals and some of the non-metals, we refer to those as the metalloids. A couple other terms to just remember from last year. The elements which are not transition elements, that's essentially the A group elements. We refer to these as the representative elements. So that's, again, everything except for those transition elements and intertransition elements. And last but not least, let's take a quick moment to recall from our previous lectures that those groups on the periodic table also correlate to orbital filling patterns and the Aufbau process. So we'll go ahead real quick and review again. Group 1A on the periodic table are all filling the first electron in an s orbital, where the principal quantum number for the last filled electron there is in the same principal quantum number as the period number. So we are going to go ahead and label that as the NS1 group. Same logic for the alkaline earth metals. We are filling the S2 orbital there, again, in the same principal quantum number as the period number, which means that is the NS2 group. And then skipping over the transition elements again, we move next to the elements with boron at the top of their group. Those are all filling the first electron in a p orbital, and therefore we refer to those as the NP1 orbital filling position. And then we're going to follow through that. You'll remember there are 6 electrons in a completely filled p orbital. So collectively, we can kind of refer to that whole p block over there as filling the NPX electron as the last filled electron in the electron configuration. And if you again remember back to the Aufbau filling sequence, if we look to those transition metals, we recall from last year that those are filling d orbital electrons. And recall that the d orbital electrons actually fill first in the 3d shell, but the first d block period is in the 4th period, which means if we're labeling these generically, we're going to go ahead and call the transition block the n-1 d position, again, because we are filling in the 4th period, where the principal quantum number would traditionally be number 4, except for we recall those d orbitals are filling 4 minus 1, or the 3rd principal quantum number for that first row. And then last down at the bottom there, our intertransition metals, as you recall from last year, are filling f orbital electrons. We can go ahead and label these as the n-2 f block, as, again, the first F block that gets filled is the 4F block for those lanthanides, but those lanthanides, again, are really part of period 6, which puts us at the 6 minus 2, or 4F position. So all that should be review from last year. We can now move on to understand the trends on the periodic table that come about as a result of the electron structure of the elements and correspondingly the shape of the periodic table. So now that we have had a look at some nomenclature of the periodic table, let's go ahead and take a look at understanding the shape of the periodic table, in particular, how those periodic trends we discussed last year relate to the table structure. As you noticed last year, the periodic table reflects a number of patterns within the properties of those elements. Those periodic properties result from the arrangement of the atoms by their atomic number and are due to the fact that the electron structure of the atoms itself is a periodic trend. And by periodic trend, again, we mean patterns that repeat themselves over and over and over within the periodic table. One thing that's useful to go back and review here briefly to get an understanding about why these patterns show up is a brief discussion of Coulomb's law. We've discussed Coulomb's law several times already. Coulomb's law relates the force of attraction or repulsion between two charged particles to the magnitude of the charges themselves and the distance which separates those charges. There is a direct relationship between the size of the charge and the force of attraction or repulsion, and an inverse square relationship between force and distance. That is, if the distance separating the charges decreases, the force of either attraction or repulsion increases. And we're going to look at these properties or trends that show up in the next couple of slides here, oftentimes referring back to Coulomb's law to gain an understanding about why the trend is the way it is. So the first trend we're going to have a look at here today is the trend for atomic radius. You may recall from your math classes that we define a radius as being the distance from the center to the outside of a circle, but that's kind of a tricky thing to do because when we're talking about atoms, atoms don't have a clearly defined outer edge due to the kind of nebulous characteristic of the electron cloud. So we need a different way of defining what we are talking about when we're talking about an atomic radius. And so we found one way of defining an atomic radius to get an idea about the size of these atoms is to take 1/2 of the distance between two adjacent nuclei in a crystalline lattice. Because although the outermost edges of those atoms are nebulously defined, the position of a nucleus is fairly measurable in terms of its position, and therefore we can get a sense of about how big atoms are by taking half the distance between two adjacent nuclei. And looking at our periodic trend for atomic radius, we see that as we move from left to right across a period, the radius of the atoms generally gets smaller. Whereas when we move from top to bottom of the periodic table, the radius of the atoms gets larger. Now, justifying this, the trend going from the top of the periodic table to the bottom, that one makes logical sense to most people because we see as we add more and more and more electron shells, the distance between those electrons to the nucleus gets larger, which makes sense because we know that as we increase the number of electron shells, we are seeing electrons existing at higher potential energy levels, which should, on average, be further from the nucleus. So kind of big idea there is that the orbital size increases as the principal quantum number increases, which leads to larger atoms towards the bottom of the periodic table. And that one makes sense for most people. The one that tends to trip people up is the trend for the atomic radius moving to the right across a period. And that one seems kind of counterintuitive because as you move to the right across a period, you're adding more protons and electrons, and we might think that adding more stuff into the atom should make it larger. But remember, as we move from left to right across the period, what we're really adding is oppositely charged particles, positively charged protons in the nucleus and negatively charged electrons in the electron cloud. And as the nuclear charge increases, as we add more and more and more protons, the force exerted on that electron cloud increases as well, because if we remember again back to Coulomb's law, there is a direct relationship between the magnitude of the charge and the force of attraction or repulsion. So we can justify then that the reason why the radius tends to decrease as we move to the right across the periodic table is because of the increasing nuclear charge, which draws in those electrons in the electron cloud closer to the nucleus according to Coulomb's law. And now, having justified those trends, we can make some generalizations. When we look for the biggest atoms on the periodic table, they're found in the bottom left-hand corner. Things like the alkali metals rubidium and cesium and the alkaline earth metal barium are very, very, very large. And when we're looking for the smallest elements in terms of the radius on the periodic table, we're looking at things like helium and then neon and fluorine as well. Now that we've had a look at the trend for atomic radius, it's time to move on next to our trend for ionization energy. Recall from last year, we defined ionization energy as the work required, or the amount of energy required, to remove an electron from a gas phase atom or an ion. And in general, the trend for ionization energy as we move from left to right across the periodic table is that the ionization energy of the elements tends to increase. Now, it's not a perfect trend. There's a couple of little bumps and blips along the way, and we can talk about why those occur with a little bit more nuanced discussion of the electron structure of the atoms. But again, in general, the trend is from left to right, ionization energy increases. As we move from the top of the periodic table to the bottom, we tend to see the ionization energy of the elements decrease. And having now defined those two trends, let's think a little bit about a justification as to why they occur. First off, moving from left to right. Recall as we move from left to right, the ionization energy increases, and in general, that's due to the increase in nuclear charge as we move across a period along the periodic table. Recall from Coulomb's law, there is a direct relationship between the magnitude on the charges and the force of attraction or repulsion between them. So as we add more protons, it is logical then that the electrons in the electron cloud are more attracted to that nucleus and therefore would be harder to remove. So that seems logical given our understanding of Coulomb's law that we would see the larger ionization energies on the right-hand side of the periodic table. And moving from top to bottom, our justification again relates to radius. Recall from our last slide that we discussed that as you move down a group on the periodic table, the orbital size increases as principal quantum number increases. That is, on average, the electrons in the outermost shells are further from the nucleus towards the bottom of the periodic table. And because those electrons are further out, they are therefore at higher potential energy, and it therefore requires less energy to remove them from the atom. That is, they're less tightly bound by that nucleus. So our general trends of left to right increasing ionization energy and top to bottom decreasing seem from that perspective to make sense. Now let's have a look at a couple of those bumps and blips along the way that seem like they don't entirely obey our trend. First off, have a look at period 2 as we move from left to right across that period in the graph on the right-hand side of your screen right now. Have a look first off at boron. Boron's ionization energy is actually lower than the ionization energy of beryllium, even though boron has a larger nuclear charge. And that seems to directly counteract what we had just discussed. But recall here we've got a more complicated system than simply attractions between the nucleus and the electrons. There's also repulsion occurring within the electron cloud, and that's what we refer to as shielding of the electrons. Because beryllium has 2 electrons in that s orbital and boron adds now a p orbital electron, the addition of those s orbital electrons causes increased shielding amongst the electron cloud, and that actually means essentially those electrons are repelling from that p orbital electron present in the boron atom, making that electron a little bit higher in potential energy and therefore a little bit easier to remove than the s electron present in beryllium. And applying that same logic, we look up again next at the blip between nitrogen and oxygen, thinking about our electron configurations there. The electron configuration for nitrogen is 1s2, 2s2, 2p3, whereas the electron configuration for oxygen is 1s2, 2s2, 2p4. And thinking about oxygen there, what we've really done, if you think about Hund's rule, is added the 4th p orbital electron there into a suborbital that was already halfway filled. And what that means is that that electron is on average closer to other electrons around it. That is, there's more repulsion amongst the electron cloud yet again, and that's going to again increase the potential energy of that electron in the oxygen atom, making it again an easier target for removal. That is, there's increased shielding, and therefore oxygen's ionization energy for its first ionization energy, the removal of that first electron is a little bit easier than it would be in the nitrogen atom. So we've had a look now at the ionization energy trends on the previous slide, and we're going to go ahead now and dive a little bit more deeply into our discussion of the idea of ionization energy. Recall we define ionization energy as the energy required to remove an electron from an atom, but other than hydrogen, atoms in the periodic table tend to have more than one electron. And that means that we can remove more than one electron from these atoms as well. So we're going to move now beyond the first ionization energy to talk about subsequent ionization energies when we remove more and more electrons. As it turns out, for each successive ionization energy in a stepwise ionization process, the ionization energy will always be greater than the ionization energies which preceded it. That is, removing the second electron is always harder than removing the first. And that should make logical sense because effectively, if we remove an electron from an atom, we turn it into a positively charged cation. And to remove a second electron from that same atom, that would imply now that we've increased the effective net positive charge on the species from what had originally been a neutral atom to now a positively charged cation. And because of that, that electron is now bound more strongly to the nucleus. In essence, what we've done is we've decreased the effect of shielding within that atom. And additionally, another thing to consider, the first electron which we remove from the atom is always the highest energy electron. That is the one which is the easiest to remove. The second electron that would be removed would therefore be a lower potential energy electron, and therefore it would be more tightly bound and would be harder to remove at that point. So the general trend of increasing ionization energy makes a whole lot of sense, just considering it's harder to take electrons from things that are already positively charged. So with that justification, we can now go ahead and have a look at an example problem that's a very popular multiple choice type question, usually on AP tests. What we're going to do here in this example is to ask you here to have a look at the stepwise ionization energy data for a particular unknown element here. And we've given you not just the first ionization energy, but the ionization energies for removing the first 4 electrons from that atom. And we've given the atom a generic letter M for some sort of unknown metal. And having a look at this here, you'll notice here, as we just discussed, that the ionization energy increases from the first ionization energy of only 580 kilojoules per mole of electrons removed, up all the way to the fourth ionization energy, which gets up to 11,600 kilojoules per mole. And the key to solving this question, to answer the kind of key questions being asked about which family on the periodic table this element belongs to, is to look at the ionization energy data and see that it's not a smooth, direct, linear relationship between the electrons being removed and the ionization energies. We see that the ionization energy increases going from the first to the second up to around 1800, and then again it increases going up to the third of around 2700. But then going from the third to the fourth ionization energy, there's a huge jump up in the amount of energy required to remove that fourth electron. And that's really here the important clue that's going to help us to answer our question. If removing the first 3 electrons was comparatively easy in comparison to the fourth, which is a huge jump up, that really tells me that there's something different going on about that fourth electron. And the logical thing to consider would be that the fourth electron is way closer to the nucleus, which would really imply that fourth electron is no longer a valence shell electron being removed. That's now a core electron being removed from the atom. And that really now tells me we must have, therefore, in this particular species, had a total of 3 relatively easy to remove valence electrons, which now tells me which family we are on the periodic table. If we've got 3 valence electrons, we really then belong in group 3 on the periodic table, 3A, which is otherwise known as the boron family. And again, this is a super popular question on the AP test. It's shown up in multiple years, so be ready for this one to show up again later in your future as well. So we've now had a look at 2 familiar properties from last year, that is atomic radius and ionization energy. And we're now going to move into a new periodic trend that is unfamiliar to you from last year's introductory chemistry class. This is a property we refer to as electron affinity. Please be very careful not to confuse electron affinity with electronegativity. Even though they sound very, very similar, these describe different periodic trends, and I want to make sure we don't mix those two up. We're going to go ahead and define electron affinity here as the change in energy associated with the addition of an electron to a gas phase atom. And from that definition, it should sound kind of logical that electron affinity is, in a certain extent, related to ionization energy. Whereas ionization energy was the change in energy associated with the removal of an electron from an atom, now we're talking about the change in energy associated with the addition of an electron to a gas phase atom. But be very careful here. Electron affinity is not simply the opposite value of ionization energy, because when you add an electron to a gas phase atom, recall that there are more electrons already present in that atom, which is going to increase the repulsive force acting on that electron. So it's not simply an inverse property of ionization energy. It's more complicated than that. When we're considering the factors that affect electron affinity, first and foremost, it should seem logical that nuclear charge plays a part here. The larger the nuclear charge, the stronger the attractive force acting upon that electron, and therefore the larger the change in energy we would expect to see as we add the electron to the atom. Now, on the opposite side of that, there's also repulsion amongst the electrons. So the nucleus is attracting the new electron which is being added, but the electron cloud itself is repelling those electrons. And so when you're thinking about an electron affinity, it's very important to consider the electron configuration of the atom which you're dealing with to see how that's going to affect your result. And a third factor that affects the electron affinity is the average distance to the nucleus of the orbital to which the electron is being added. Obviously, if you're adding an electron to a large atom that's got a valence shell which is a long ways away from the nucleus, you're not going to get that new electron as close to the nucleus, which means it's going to be less energetically favorable to add that electron. That is, you're going to have a less exothermic process probably. Whereas if you had a much, much smaller atom in which the valence shell is closer to the nucleus, the electron affinity would then probably be a larger, more exothermic value as you add that electron to that atom. So one other thing to consider here is that whereas ionization energies are always an endothermic process, that is, it requires energy to remove electrons from atoms, for electron affinity, whether it's exothermic or endothermic kind of depends on the situation you're dealing with. For many atoms, for most atoms, the addition of an electron to that atom is going to be an exothermic process because you're bringing an electron closer to a nucleus, which is energetically favorable. And the effect of the repulsion amongst the electron cloud is generally smaller than the nuclear charge as attraction to that newly added electron. That being said, if you added a second electron to an atom, in that case, now the electron cloud is more negative overall with an extra electron present on it already. So additional electron affinity steps are going to be increasingly endothermic. That is, it's going to start to require energy to add those electrons to the now negatively charged ions. So, with that definition of electron affinity taken care of here, let's go ahead and have a look at a type of question that we might expect to see the AP test asking us here. So in example number 2, it's asking us to predict the order of the increasingly exothermic nature of the electron affinity for the elements in the halogen family. That is, from a thermodynamic standpoint, a increasingly negative change in energy, because remember, an exothermic process is going to be one in which we see a negative change in internal energy of the system. That is, the system is going to a lower potential energy. So again, we're looking for the increasingly exothermic nature of the electron affinity for the elements in the halogen family here. So if we're going to be making a quick prediction here, it seems logical to assume, given the definition we just discussed and the factors which affect electron affinity, that fluorine, being the smallest of those different elements and the one which we already know seems to have a very, very strong attraction to electrons, is going to be the element here which has the most negative electron affinity. That is the one that is the one which from a thermodynamic standpoint would be the most favorable. And on the opposite end of that, the largest of those elements there, iodine, we might expect that to have the least negative electron affinity, because iodine as a larger atom is going to, number one, have a lot of repulsion amongst the larger electron cloud with all those electrons flying around out there. And also, we're not going to be adding that electron to an orbital which is close to the nucleus on average. So if I was going to be predicting here, I would probably say, going in order of increasingly exothermic, I would say, well, probably iodine is going to be the least exothermic, so I'll give that a number 1 for my guess. Bromine is going to be a number 2. Chlorine is getting a number 3 as we get smaller and smaller as these atoms go. And fluorine is going to be a number 4. So that's my prediction right now. Now, having made that prediction, as it turns out, I'm in for a bit of a surprise. Looking at the actual data here, I find that the electron affinity for iodine is negative 295 kilojoules per mole. For bromine is negative 325 kilojoules per mole. So far, so good. Looks like my prediction is looking great. Chlorine is negative 349 kilojoules per mole, still on track. And fluorine, my guess for the most exothermic of these electron affinities, is only 328 kilojoules per mole, as it turns out. And that's a big surprise. So probably rather than having you just simply guess what the electron affinities were for these atoms, the AP test is going to be more likely interested in your ability to justify why there's kind of an anomaly going on here, something other than we would initially have predicted. And to consider what's really going on, let's think for a moment about why fluorine is not the most exothermic electron affinity present here. If you think about properties of fluorine, one of the first things that comes to mind is that fluorine is a really, really, really small atom. And as a really, really, really small atom in the upper right-hand corner of the periodic table, if we add another electron to that very small atom, because all those electrons are so tightly packed around the nucleus, the addition of that extra electron is probably going to run into a large amount of repulsion from the other electrons which are there tightly packed together. So we can justify there that it's likely fluorine really is actually almost too small to see a very large negative exothermic electron affinity in comparison to something like, let's say, chlorine. So the actual order we see there is iodine 1, bromine 2, and then let's see, fluorine 3, it's close to bromines as it turns out, and then chlorine is number 4. That is the halogen with the highest electron affinity. So, having now taken care of a discussion of that new term electron affinity, we're going to go back to something which you learned about last year for our last periodic trend to discuss here today, which is electronegativity. If you recall from last year, we defined electronegativity as the numerical value that reflects the ability of an atom to attract electrons to itself as part of a covalent bond. Or we kind of gave you a way of thinking about it as more or less a reflection of electron greediness. Whereas ionization energy and electron affinity are both trends that have to do with changes in energy, electronegativity is not actually an energy value. It's actually usually defined in terms of what's referred to as Pauling units, which are kind of proportional values that show how able atoms are to attract electrons to themselves. And if we want to have a look at the trend for electronegativity on the periodic table, as we move from left to right across a period, in general, the electronegativity increases until you get to the halogen family and then drops down to essentially 0 when you get to the noble gases. And as you move down a group on the periodic table, the electronegativity generally decreases. So looking at those two trends, we recall from last year that the atom on the periodic table with the highest electronegativity was fluorine, with an electronegativity of around 3.98 Pauling units. And on the other hand, we have the atoms with the lowest electronegativity on the bottom left-hand side of the periodic table, things like cesium or francium, both of which have electronegativities right around 0.7 Pauling units. And we can justify the trend which we observe right there by thinking first about nuclear charge again. As we move from left to right across the periodic table, the nuclear charge increases, which means those atoms are going to have a better ability to exert an attractive force on other atoms' electrons due to the increased number of protons in their own nuclei. And secondarily, also remember as we move to the right across the periodic table, those atoms are getting smaller, which means they can approach other atoms more closely and therefore, by Coulomb's law, exert a larger attractive force on those other atoms' electrons due to the inverse square relationship between distance and force. And likewise, as you move down the group on the periodic table, those atoms are getting larger, which means that they have a decreased ability to get close to other atoms. And therefore, the attractive force they can exert on those other atoms' electrons decreases, diminishing again because of the inverse square relationship described in Coulomb's law. So again, the king of electronegativity on the periodic table is fluorine. That element is fantastic at grabbing electrons away from other atoms when they are shared together in covalent bonds. So we've now provided for you a justification and a little bit more nuanced understanding of the periodic trends on the table than you got last year in your general chemistry class. You can expect to see questions relating to periodic trends pop up on pretty much every year's AP chemistry test. And that brings us to the end of our discussion for this lecture. Thanks for listening.